Hello students and welcome to the course Urban Rail Transit Tracks, Stations and Yards. In the previous lesson, we had learned the different types of the joint used to connect sections of the rails so that the length of the track can be extended. However, a rail joint is the weakest part in the track. At the joint, there is a break in the continuity of the rail in both the horizontal and the vertical planes because of the presence of a gap. The basic purpose of the gaps was to absorb length variations due to the temperature variations. Meanwhile, they significantly reduce passengers' comfort by generating lots of noise pollution and vibration and cause considerable wear and rail fatigue and wear. Maintenance expenses, therefore, greatly increased, including 30% extra labor required for maintenance of the joint. And extra power is required by the train to overcome resistance generated by these joints. In this lesson, we're going to carry on with the rail joints to see how drawbacks of the gaps are addressed. Theoretically, the longer is the rail, the lesser will be the number of the joints and the fitting required by the lesser the cost of the construction and maintenance. There have been advances in technology that have improved the performance and the safety of the railway joints. Continuous welded rail, also known as the CWR, sometimes referred to as the ribbon rails, are widely used in modern railways. CWR eliminates the need for most conventional joints, reducing the amount of maintenance required and improving the ride quality for passengers. The first welded track was used in Germany in 1924 and has become common on main lines since the 1950s. Due to the absence of traditional joints, CWR tracks boast remarkable durability, ensuring the seamless journey for trains and demanding less maintenance. This unique design allows trains to achieve higher speeds while minimizing friction. The advantages of CWR extended beyond a smooth ride and enhanced speed capabilities. The absence of conventional joints significantly reduces the need for track maintenance, including tasks such as bolt tightening, component replacement, and joint lubrication. Furthermore, the implementation of CWR leads to decreased train-generated noise as they traverse the track. Although the initial installation cost of the CWR surpasses that of a fish-plated track, the benefits prove substantial. The reduced maintenance expenditures for the track, combined with improved stability, elevated running speeds, reduced power consumption, and enhanced passenger comfort, ensured a favorable return on the initial investment. Notably, CWR introduces a heightened level of passenger comfort, considerably slower evolution of track defects, decreased fatigue in various track components, and lower stresses in both wheels and rolling stock. As mentioned earlier, the rail joint stands out as the most vulnerable point. So the best remedy for the problem caused by the rail joints lies welding the rails. The purpose of the welding is to join rail ends together by the application of heat and thus eliminate the negative effects of the rail joints. So welded joints are widely used in CWR tracks. In CWR track, the rails are welded together by utilizing different techniques of welding to form one continuous rail that may be several kilometers long. There are 4 welding methods used on railways: thermite welding, electric arc welding, flash butt welding, and gas pressure welding. Now let's check them out one by one. Thermite welding of rails. The thermite welding is the only form of site welding which is being adopted universally. The method was first developed by Hans Goldschmidt, a German chemist, towards the end of the 19th century. The principle behind this process is that when a mixture of finely divided aluminum and iron oxide, called thermite mixture, is ignited, a chemical reaction takes place which results in the evolution of the heat and the production of iron and aluminum oxide. In this reaction, 159 grams of iron oxide combines with 54 grams of aluminum to give 102 grams of aluminum oxide, 112 grams of iron, and 182 kilocalories of heat. The reaction is exothermic and it takes about 15 to 25 seconds to achieve a temperature of about 2,500 degrees Celsius. The released iron is in the molten state and welds the rail ends, which are kept enveloped in the molten boxes. The aluminum oxide, being lighter, however, floats on the top and forms the slag. Because the thermite iron obtained from such a reaction is too soft for the practical use, steel-forming alloying additions are added to the thermite mixture to harden and improve wear resistance, while cold metal reduces the reaction temperature and improves the steel yield. Electric arc weld. During electric arc welding, a weld is slowly created inside in a copper casting using electrode that start from the rail base. This process takes about 15 to 20 minutes and includes steps like placing the casings, warming the parts to 200 and 250 degrees Celsius using propane burners, welding the gap from the bottom upwards, and finally taking off the casings. However, the quality of this welding method isn't very good, so it's only used when thermite weld is not possible. Flash butt welding. Flash butt welding works by using electricity to heat two pieces of metal until they become soft enough to be pressed together. This pressing action creates a strong bond between the two pieces, creating a single piece of metal. The heat used for this process is created by the electric current that passes through the contact points as the pressure is applied. This process can be done with different metals such as aluminum, copper, iron, and steel alloys. Flash butt welds are generally produced in welding depots with stationary welding machines. In terms of quality, flash butt welds are better than thermite welds, and now mobile flash butt welding machines are invented so that these welds can be made on the track. When working with flash butt welding, there are several factors to consider, including the voltage required for the job, electrode force needed for an effective weld, and the joint preparation before starting the weld. All these elements need to work together correctly in order for the weld to be successful and long-lasting. What's more, although the metallurgical weld quality, as represented by the fatigue strength produced by the mobile machine, is equivalent to produced by the stationary machine, it's not easy to achieve good geometrical properties. Gas pressure welding. In gas pressure welding, the necessary heat is produced by the combination of oxygen and acetylene gases. The rail ends to be welded are brought together and heat is applied through the burner connected to oxygen and acetylene cylinders by means of rectangular end tubes. A temperature of about 1,200 degrees Celsius is achieved. At this temperature, the metal of the rail ends melt, resulting in the fusion and welding together of the ends. The rails to be welded are clamped at the wall by applying the pressure of 40 tons, heated to a temperature of about 1,200 degrees Celsius to 1,400 degrees Celsius, and bodied with the opposite pressure about 20 tons. Then the joint is again heated to a temperature of 850 degrees Celsius and allowed to cool naturally. It has been said that this method of welding is cheaper as compared to flash butt welding. The quality of this welding joint is also claimed to be quite good. There are both stationary and mobile units available for gas pressure welding. The use of CWR improves passenger comfort and results in a substantial decrease in the total life cycle cost. But it doesn't only have advantages. In conventional non-welded track, The rails are connected by means of a gap of joints to allow for the length changes caused by temperature fluctuation, preventing the development of axial forces and the consequent risks of track buckling at high temperature. However, CWR can contribute to a rail buckling under certain conditions when the rail deforms or wraps due to the thermal expansion or contraction. A rail track without a joint gap is liable to get distorted, particularly in hot weather when the compressive forces in the track exceeded the lateral or longitudinal resistance of the track. The buckling of the track is a matter of grave concern as may lead to the derailments and even serious accidents. To avoid stresses which can cause rail buckling, expansion joints are applied in CWR to allow for the expansion and contraction of the rail due to changes in temperature. Structures of expansion joints are different from place to place. They are only used in joint tracks near the movable bearing of very large structures at the end of CWR track or changes in structures such as switches, crossings, and bridges. Some expansion joints consist of two jaw and tongue rails, which can move against each other. And some expansion joints include the fixed stock rail and the switch rail, where the switch rail can move parallel to the stock rail over a maximum distance of 220 millimeters. Apart from using expansion, CWR is laid and fastened in a temperature roughly midway between the extremes experienced at that location, and this is known as the rail neutral temperature. This is because the steel rail contracts at the low temperature and expands at the high temperatures. In extreme cold, a rail of CWR suffers tensile stress, which can cause rail to fracture. In extreme heat, the length of CWR suffers compressive stress, which can cause rail buckling. In summary, rail joints in urban transit systems have historically posed challenges, including noise, maintenance cost, and wear. Continuous welded rail has emerged as a solution, eliminating most rail joints and offering numerous benefits, such as improved passenger comfort, operation efficiency, and reduced maintenance cost. Various welded methods are used to create CWR, with flash butt welding being notable for high-quality welds. However, CWR can lead to rail buckling in extreme temperatures, necessitating the use of expansion joints. Overall, CWR has revolutionized urban transit, providing a smoother, quieter ride and cost savings. While careful consideration of temperature-related challenges is essential for its successful implementation. Alright, that's all for contents in this lesson. Until next time.